Hello everyone. So for today's presentation, I'm going to be presenting on Hippocrates' Quadrature of the Lune, and my name is Alma Mejia. So the first thing I'm going to be talking about is how did mathematics began. So nobody really knows where mathematics began, but they do know that the invention of agriculture in 15,000 to 10,000 BC, humans had to address the two fundamental concepts of mathematics, which were multiplicity and space. So humans or people, they used the concept of multiplicity when counting sheep or distributing crops. So anything they will do around their farm, like with animal and planting and everything, like all of those things, they had to count. So that's where the multiplicity came from, and also the space, how much space did they had. They had to manage their space very wisely. And over the centuries, these ideas evolved into arithmetic and later into algebra. And the first farmer would have needed insights carried on through history, which became geometry. So nobody knows exactly where the math began, but they just know that it goes from way back when agriculture began. So next are the Egyptians. So archaeological records indicate that by 2000 BC, the Egyptians had primitive numeral systems as well as geometric ideas about triangles, pyramids, and the like. So for instance, this figure that we see here, figure 1.1, is very interesting. So what the Egyptian architects used to do, they used to get 12 segments of rope that were the same, so they were equal of the length. And they used to get these ropes and stretch them out to make a triangle. So for one side of the triangle, they would stretch out 5 ropes. For the other side of the triangle, they would stretch out 4 ropes. And then for the bottom part, they would stretch out 3 ropes, which is very, very similar to us as we know the Pythagorean theorem. They didn't really know this was going on when they did this, but they used it to make their right angle triangles for their pyramids. So that's where the concept began. So the implicit of this construction is the understanding of the Pythagorean relationship of right triangles. So the Egyptians seem to know that a triangle with sides length 3, 4, and 5 must contain a right angle. So as we know, the Pythagorean tell us that if we have a right triangle, then it means that a square is equal to b squared plus c squared. But from what they learned it a little bit opposite. They went for the numbers first. So they learned that if we had a squared is equal to b squared plus c squared, then therefore we have a triangle. So like in this figure here, if we had a squared plus b squared plus c squared, then we had triangle BAC. Okay, so Thales of Miletus, this is a very important person here. So around 600 BC, in the town of Miletus on the western coast of Asia Minor, there lived the great Thales. So Thales was credited with being the father of demonstrative mathematics. He was the first scholar who supplied the why along with the how. And there's not really any evidence of his life, but they do know different stories that were just carried on along the way in different legends. So there was a story about him that they said that he did not want any children and he didn't want to get married, and he was more like kind of like a sour person. And he just would express himself really strongly. So many people describe him as like a mean person or something like that. But regardless, he did earn his reputation in mathematics from his insistence that geometric statements not accepted simply because of their intuitive plausibility, but instead it had to be logical proof to it. So he is known as one of the earliest mathematicians. And so his thing was he did not want to believe anything unless it was proven, which now we have a lot of different proofs of different mathematical theorems. And that was more of like his thing there, that he did not want to believe something until it was proven. And tradition holds that it was Thales who first proved the following geometric results. One being the vertical angles are equal. The next one was the angle sum of a triangle. It equals to two right angles. And the base angles of isosceles triangles are equal, and an angle inscribed in a semicircle is a right angle. Okay, and then a very important mathematician also is Hippocrates of Chios. So Hippocrates was born on the island of Chios sometime in the 5th century BC. And a legend has it that Hippocrates earned his reputation after being defrauded of his fortune by pirates who apparently took him for an easy mark. So he was had his money he had his money stolen. Um, and needing to make financial recovery, he traveled to Athens to begin teaching. So he was one of the first persons who actually began teaching in order to get an income. And Hippocrates is remembered for two signal contributions to geometry, and one being the composition of the first elements, and two being the quadrature of the lune. So remarks on the quadrature. So the quadrature, or squaring a plane figure, is the construction only using compass and straight edge of a square having area equal to that of the original plane figure. If the quadrature of a plane figure could be accomplished, we say that the figure is quadrable or squarable. So I will be showing some figures to show you exactly what this means. And on top of that, the Greeks, they were really fascinated with the quadrature. So those who thought a natural world governed by reason and order, there was much appeal in the process of replacing the asymmetric with the symmetric and the imperfect by the perfect, the irrational by the rational. So the first thing I'm going to be talking about is the quadrature of a rectangle, and this is called, they called it step one. So our goal here is to show that in this figure 1.7 that this rectangle that you see shaded will have the same area as the square that is shaded there. And that's what Hippocrates was trying to prove. He was trying to prove that any figure, anything that we have like square, circle, triangle, all of that has the same area of a square. So first he let BCDE be an arbitrary rectangle. So the rectangle that you see here. And we want to construct with a compass and a straight edge only. We want to construct a square having the same area equal to the rectangle as I just stated. So with a straight edge, extend the line BE to the right. So BE is right here, and we're going to extend it to the right a little bit, and then we get our line segment EF. So then we know EF is equal to ED. So EF is equal to the line segment ED. Next, we want to bisect BF. So BF is right here. We're going to bisect it at G, and with the center being G here. And then the radius is going to be BG is equal to FG. And we're going to do a semicircle as shown here in the figure. So then finally at E, we're going to construct a line EH. So E is right here, and we just do a line EH from here. And that's going to be perpendicular to BF, that is right here. And then H is the point of intersection of the perpendicular, and the semicircle is in the form. So finally at E, construct a line EH perpendicular to BF, which is right here, where H is the point of intersection of the perpendicular and the semicircle. And from there construct the square EKLH. So we're going to do this square here. So now there's a claim that the shaded square having the side of length EH, a figure we just constructed, has the same area equal to the original rectangle BCDE. So this was just what they were trying to show. But next, I'm actually going to show the proof of how they got it. So I forgot to add a title here, but this is the proof. So as the book states, to verify this claim requires a bit of effort. So for notational convenience, we're going to let A, B, and C be the length segments HG, EG, and EH respectively. So then we have this triangle GEH here. So since triangle GEH is a right triangle by construction, the Pythagorean theorem gives us that a squared is equal to b squared plus c squared, or equivalently, a squared minus b squared is equal to c squared. Now, clearly the line segment FG, which is here, is equal to the line segment BG here, which is equal to the line segment HG, which is equal to A, since all are radii of the semicircle. So right here. Thus, the line segment EF here is equal to the line segment FG right here minus EG which is right here. So FG minus EG, which is also equal to A minus B. And then the line segment BE right here is equal to the line segment BG minus, that's actually plus, so BG plus GE, which is equal to A plus B, which is this little a here, and then plus B. So now that we have everything kind of just written down, it follows that the area of the rectangle BCE is just the length times or L times W, right? So our base here is the line segment BE, and our height is the line segment ED. So when we multiply those two, we know that it's equal to A plus B times A minus B, which is equal to A squared minus B squared, which is just equal to C squared. And that is the area of the square EKLH. And hence we have our proof that the area of the rectangle is the same as the area of the square. So the next thing that Hippocrates wanted to prove on was the quadrature of a triangle. He wanted to see that the triangle also had a square that has the same area as the triangle. So the proof started something like this, which was given the triangle BCD, you're going to construct a perpendicular from D meeting BC at a point E. So this triangle here, we're just going to do a line here starting from D going all the way down, and we end at E. So then we're going to call the line segment DE. This is the altitude or the height. And to know that the area of the triangle is 1/2 times base times height, as we already know. And here it's going to be 1/2 times the line segment BC, which is our base, and then times the line segment DE, which is our height. So if we bisect DE at F, so here we're just going to put a dot right in the middle of DE and construct a rectangle with the line segment GH, which is here the base of the rectangle. This rectangle is going to be equal to the line segment BC of this triangle here, and the line segment HJ is going to be equal to the line segment EF. So this little part here, HJ, is this part here, EF. And we know that the rectangle's area is the line segment HJ times GH, which is equal to the line segment EF times BC, which, as we know, is equal to 1/2 DE times BC, and that is the area of the triangle. So now that we know that the area of the triangle is the same as the area of the rectangle, then we could just go back to the step 1, and we could see that we could find the area of the rectangle and find the square of the same area. So if that square has the same area of the rectangle, then we could conclude that the triangle will have the same area of the square. And this completes the quadrature of the triangle. So after the proof of the quadrature of the triangle, Hippocrates also proved that there's a quadrature for of the polygon. I decided to skip that part because it was going to be a little too complex. It was a little hard for me as well, and it's just much longer than these two proofs, so I decided to omit that part. So the next thing I'm going to move on is the quadrature of the lune, and this part is actually very interesting. So what is a lune? A lune is a plane figure bounded by two circular arcs that is a crescent. So it's almost like when you see a moon and it's like kind of like that little U shape. That's pretty much the lune here. Hippocrates did not square all such figures, but rather a particular lune he had carefully constructed. So his argument rested upon three preliminary results. So one was the Pythagorean theorem. An angle inscribed in a semicircle is right, and the areas of two circles or semicircles are to each other as the squares on their diameters. So the first two were already known, but it was the proposition, it was the last proposition that was considered more sophisticated. So for instance, if one semicircle has 5 times the diameter of another, the former has 25 times the area of the latter. So that's what he was trying to say here. So this is more of a proof of the areas, that the areas of two circles or semicircles are to each other as the squares of their diameter. So we're going to consider Hippocrates' proof. And first we're going to begin with a semicircle having the center O. So we have this semicircle here, and it has center O. The radius AO here is equal to OB here. which is pretty obvious. And then we're going to construct OC perpendicular to AB. So OC is right here, and that's perpendicular to AB, right in the middle. And with the point C on the semicircle, and draw lines AC and BE. So we're just going to draw this like dotted lines here, AC and BE. I meant to put AC and BE, sorry, not BE. So then we're going to bisect AC at D, so this dot here that you guys see, and using AD as a radius and D as the center. So this is our center here, and we're using AD as a radius. We're going to construct a semicircle. So we're doing a semicircle here, which is part of the dark area, the dark shaded area, and then the part that has no color. So that's our big semicircle, and with the F here, the curve you guys see, this will create the lune AECF, which is the shaded part. And Hippocrates' plan of attack was simple yet brilliant. So he first had to establish that the lune in question had precisely the same area as the shaded triangle AOC. And then with this, he could conclude that if the lune here, that this dark shaded area was the same area as the triangle, we already know that we could find a square that has the same area as that triangle. Therefore, that square will have the same area as the lune. So this is the proof of the theorem lune ACEF is quadruple. So first we're going to note that the angle ACB is right since it's inscribed in a semicircle. So then we have triangles AOC and BOC, and they are congruent by the S side angle side congruence. And we have that the line segment AC is equal to BC. So with that being said, we could use the Pythagorean theorem, and we could say that the line segment BAC squared is equal to the line AC squared. I'm sorry, the line segment AB squared is equal to the line AC squared plus BC squared, which is equal to 2 times the line segment AC squared. And because AB is the diameter of the semicircle ACB and AC is the diameter of the semicircle ACE, which is right here, then we could use the principle that we stated before. So then the area of semicircle AEC over the area semicircle ACB is equal to the line segment AC squared over the line segment AB squared, which is equal to the line segment AC squared over 2 times the line segment AC squared, and then that just gives us our answer of 1/2. So in other words, the semicircle AEC has 1/2 of the area of the semicircle ACB. So once again, here's the semicircle ACE right here, and what it's saying that it has 1/2 of the area of ACB, which is right here, ACB, right there. So that's like 1/2 of it. But we now look at the quadrant AFCO. So this is like a quadrant here, this part here, which is the little triangle, and then the non-shaded area. So we look at that quadrant here, and clearly this quadrant also has 1/2 of the area of the semicircle ACB, which is this other 1/2 here, and then this is the other 1/2. And so then from that we could conclude that the area of the semicircle or AEC, is equal to the area of the quadrant AFCO, which is right here. And then finally, we need to subtract from each of these figures their shared region AFCD. So here in the other figure, figure 1.16, we know that we could say that the area of the semicircle AEC minus the area of the region AFCD, that is equal to the area of the quadrant AFCO minus the area of the region AFCD. So pretty much we're saying that this Lune right here, this Lune, the dark part, is the area of that is equal to the triangle, that the little shaded area here. So all we're subtracting is this little portion here of the Lune, and we're taking that piece off, and we're doing the same thing for this quadrant, taking this little small piece off here, this little small semicircle, and then we could conclude that this Lune here is the same area as the triangle here. So then we get that the area of the Lune is the area of the triangle ACO, and quick look at the diagram verifies that this amounts to. But as we have seen, we can construct a square whose area equals the triangle, and thus equals that of the Lune as well. So as we said before, we could construct a square that has the same area as this triangle. And if that square has the same area as this triangle, then that square must have the same area as the Lune, which is actually very interesting to me. So then the next question, that mathematicians became more excited on was, well, is there a quadrature of a circle? So Hippocrates had already established that there was quadrature for a square, quadrature for a triangle, and then quadrature for polygons. So now, and also the quadrature of the Lune, and now mathematicians wanted to know, well, is there a quadrature of the circle? So there was actually an attempt to prove this, and it was looking pretty well until they had found that there was a flaw on a proof that was made. So during many years passed, and they still had not found the proof if there was a quadrature of a circle. So after 2,000 years of trying, it was believed that maybe the quadrature of a circle was just impossible. And at last, in 1882, there was a German mathematician, Ferdinand Liedman, and he succeeded in proving that there in fact was no quadrature of a circle. So this was like impossible. And this became a theorem which state that the quadrature of a circle is impossible. So that's so during this time, the mathematician Liedman, he took up on the problem, and he wanted to show that there was no quadrature of a circle with numbers. He wanted to do it more in the algebra way. So first he took up on pi, the number pi, and he said that pi was not constructible. Hence, the square root of pi is not constructible. So he used this observation to conclude his proof. And his proof went something like this. So first he states, let's assume, for sake of eventual contradiction, that circles can be squared. So he did this proof as contradiction. And so we get our compass and easily construct a circle having the radius r equals 1. Its area is thus pi r squared, which is just equal to pi since our radius is 1. So if circles are quadruple, as we have temporarily assumed, then we employ our compass and straight edge work, and then we start doing the arcs and drawing lines. Eventually, after only a finite number of each such steps, end up with a square and also an area pi. So we're just trying to see that we're kind of like pretending that we went through all the steps and then we ended up with this square, as we say. But then the square also has area pi, and we're going to use this figure here, 1.1. And as we know that to take the area of a square, we need the length times the height. So then we're going to call the length of the square the side x, and then we will see that pi is equal to the area of the circle, since we are assuming that a circle is quadruple. And therefore it equals to the area of the square, which is equal to x squared. And so the length x is equal to square root pi, since we just squared both sides. But we see that x equals square root pi would be constructible with compass and straight edge, but as we noticed before, the construction for square root of pi it's not possible. So this already is a contradiction, and tracking back through the argument and looking for the source of the contradiction, then we can find not only the initial assumption, namely the circles can be squared. So as a consequence, we must reject this and conclude once and for all that the quadrature of the circle is logical impossibility. So that's pretty much how his proof went. He wanted to show that there was a quadrature of a circle with numbers, more like arithmetic in the algebra way, and that's what he used pi, since we know that the area of a circle is pi r squared, and he used, which we all know, the area of a square is just length times width, and which is just x squared, and therefore we just couldn't conclude this. So that's pretty much how his proof went, and that was pretty interesting to me. But yeah, that concludes my presentation. There's not going to be any homework problems, since we know Dr. Larson and I know that you guys will be working on the term paper. So no homework problem for this, but if you guys do have any questions, then you could reach out to me. So the book used was The Journey Through Genius by William Dunham. And I went through the first chapters of the book and it was pretty interesting, so I would suggest you guys take a look at the book as well. But yeah, that concludes my presentation. Thank you.